Hello friends, welcome you all on my YouTube channel JK Academy India. In this video, we will discuss about the speed control of three-phase induction motors. A three-phase induction motor is practically a constant speed machine, more or less like a DC shunt motor. Speed regulation of an induction motor having low resistance is usually less than 5% at full load. There is one difference of practical importance between the two, where a DC shunt motor can be made to run at any speed within the wide limits with good efficiency and speed regulation merely by manipulating a simple field rheostat. The same is not possible with induction motors. In their case, speed regulation is accompanied by a corresponding loss of efficiency and good speed regulation. That's why it is much easier to build a good adjustable speed DC shunt motor more than an adjustable speed induction motor. Different methods by which speed control of induction motor is achieved may be grouped by two main headings. First is the control from stator side and second is control from the rotor side. Control from the stator side by changing the applied voltage, number of stator poles, or by changing the applied frequency. Control from rotor side involves rotor rheostat control by operating two motors in concentration or cascade and by injecting an EMF in the rotor circuit. A brief description of these methods would be given below. That first we will see changing applied voltage. It is the cheapest and easiest, is rarely used because a large change in voltage is required for relatively small change in speed. So there is no big impact of applied voltage on the speed. This large change in voltage will result in large change in the flux density, thereby seriously distributing the magnetic condition of the motor. So we know that the flux density in three-phase induction motor B equals to voltage applied by the frequency of the supply voltage. So if we are reducing the applied voltage, ultimately we are reducing the flux density. So somehow it is creating seriously disturbing magnetic condition in the motor. Now the second method, changing the applied frequency. As you know, in case of DC induction motor, the speed Ns equals to 120 F upon P. So the speed of an induction motor can be changed by changing the supply frequency. This method could be used in cases where the induction motor happens to be only load on the generators. in which case the supply frequency could be controlled by controlling the speed of the prime movers of the generators. But here again the range over which the motor speed may be varied is limited by the economical speeds of the prime mover. This method has been used to some extent on electrically driven ships. So when the there were no variable frequency drives were in existence, that time in ships this technology was used, means generators which generates the electricity were run accordingly on the desired frequency to control the connected AC induction motors. And after development of VFD, it has been discontinued because it is also a costly method. Second, third is the changing of number of stator poles. Easily applicable to the squirrel cage motors because the squirrel cage rotor adapts itself to any reasonable number of stator poles. From the equation, it is also clear that synchronous speed of induction motor could also be changed by changing the number of poles, because speed is equal to 120 F by number of poles P. So by changing the number of poles, we can change the speed of the motor. This change of number of pole is achieved by having two or more entirely independent stator winding in same slots. Each winding gives different number of poles and hence different synchronous speed. For example, a 36 slot stator may be having 3-phase winding, two 3-phase winding, one with 4 pole, another with 6 pole. With a supply frequency 50 Hz, 4 pole winding will give speed 1500 rpm and 6 pole winding will give speed of 1000 rpm. Motors with 4 independent stator windings are also in use and they give 4 different synchronous speeds. Of course, one winding is used at a time and others being entirely disconnected. This method has been used for elevator motors, means lift, traction motors, and also for small motors driving machine tools. Speeds in the ratio 2:1 can be produced by a single winding if wound on the consequent pole principle. In that case, each of the two stator windings can be connected by a simple switch to give two speed, each which means 4 speed in all. For example, one stator winding may give 4 or 8 pole and other 6 or 12 pole. For a supply frequency of 50 Hz, 4 speeds 1500 rpm, 750, 1000 and 500 rpm can be achieved. Another combination commonly used is two group 2 and 4 pole winding with 6 and 12 pole winding, which gives synchronous speed 3000, 1500, 1000 and 500 rpm. Now, the fourth method is rotor rheostat control. In this method, which is applicable to only slip ring motors alone, the motor speed is reduced by introducing an external resistance in the rotor circuit. For this purpose, the rotor starter may be used provided it is continuously rated, or it may be of S1 duty. This method is in fact similar to armature rheostat control method of DC shunt motors. So as shown in a picture, this is a starting rheostat speed controller connected to the slip ring, and slip rings are having connection of the winding of the rotor, and this is the stator. A three-phase supply is given to the stator. So near synchronous speed, for very small slip value, we can say torque is proportional to S by R2, where R2 is the rotor resistance, S is the slip. It is obvious that for a given torque, slip can be increased, that is, speed can be decreased by increasing the rotor resistance. One serious disadvantage of this method is that with increase in rotor resistance, I square R copper loss also increase, which decreases the operating efficiency of the motor. In fact, the loss is directly proportional to the reduction in the speed. The second disadvantage is the double dependence of speed, not only R2 rotor resistance but on load as well. Because the wastefulness of this method, it is used where speed changes are needed for short period only. So in this video we have discussed the types and methods how we can control the speed of three-phase induction motors. Now in next video we will discuss about the variable frequency drives used to control the speed of three-phase AC induction motors. So till then, take care and goodbye.